Hey everyone, this is the first video in a several-part series which will cover non-finite, procedurally generated mazes in Unity. I'm going to provide you with a detailed explanation of the Eller's maze algorithm and a step-by-step guide on the coding process within Unity. In later episodes, we will also integrate real-time maze generation in relation to a player's position, showing up potential game usage for these mazes. The video you're watching right now will only cover the explanation of the algorithm, which is essential for understanding the later videos. The rest of the videos in the series will be much more in-depth on the actual programming in Unity. I am now going to explain the Eller's maze algorithm, and I'm going to go over each step to how the maze is generated. My explanation is entirely based off a paper from neocomputer.org. It is highly detailed, provides each step of the algorithm with visuals, and is easy to follow. So if you want to follow along during my explanation, as I will be regularly referencing it, or if you want to read it yourself to get a better understanding, I highly suggest you check out the link in the description. There are 5 main steps to our algorithm, but before we start getting into them, we should cover the maze layout and some terminology. Our maze is going to be arranged and placed on a grid, with each cube representing an individual cell of the grid. In this example, we have an empty 10 by 10 grid, meaning 100 total cells comprise it. Our maze will be generated on this grid, one row at a time, from top to bottom. Now that we understand the basics, let's jump into the algorithm steps. The first step of the algorithm states as follows. Create the first row. No cells will be members of any set. This first step is pretty simple and will only ever apply to the first row of the maze. For step 1, we will create an empty row with X number of cells, with X representing how many cells long our row will be. For this example, we will create an empty row of 10 cells as our grid length is 10. For the second part of this step, we will not assign any of these cells to a set. Now sets are simply how we're going to organize and differentiate cells in the grid. In our example, sets will be represented as numbers. Join any cells not members of a set to their own unique set. This step is saying that if there are cells with no set value assigned, assign a new unique set value to that cell. Because we have a row of cells without any set values, we're simply going to give each cell their own unique set value. In this first row, we're just going to assign values 1 through 10 going left to right. Step 3 is where the steps become a bit more involved and where we start to place the vertical walls of the maze. Create bottom walls moving from left to right. Randomly decide to add a wall or not. If the current cell and the cell to the right are members of the same set, always create a wall between them. If you decide not to add a wall, union the sets to which the current cell and the cell to the right are members. So to start this process, we're going to loop over each cell in this row, starting from the leftmost cell going right. The second bullet point, which is checking whether the two cells are the same, is actually going to act as the prerequisite to deciding whether to add a wall or not. We're going to compare the current cell we are looping over and its right neighbor cell. If the two cells are members of the same set, always place a wall between them. If they are not members of the same set, we are going to randomly decide to place a wall between the cells or join the cell sets. This random percentage can be whatever we want it to be, meaning we can set biases towards having more vertical or less vertical walls in our maze. However, for simplicity's sake right now, it will be a 50-50 chance for placing the wall or joining the sets. When joining the cells, the right cell takes the set of the cell we are currently looping over. Now, let's go back to our row after step 2 and apply step 3 to each cell in the row. Step 4. Create bottom walls, moving left to right. Randomly decide to add a wall or not. Make sure that each set has at least one cell without a bottom wall. If a cell is the only member of its set, do not create a bottom wall. If a cell is the only member of its set without a bottom wall, do not create a bottom wall. Step 4 is similar to step 3 in a lot of ways. For step 4, we will be looping over each cell, starting from the leftmost cell, going right. The bottom bullet points, again, act as prerequisites to adding a wall or not. If the cell is the only member of its set without a bottom wall, meaning every other cell in that set already has a bottom wall, then don't add a bottom wall to that cell. If a cell is the only member of its set, do not create a bottom wall. If neither of these 2 points apply, then we will randomly decide to add a bottom wall or not to the cell. And again, we can set this randomness to whatever we want it to be, but for simplicity's sake, it will be a 50-50 chance to add a wall or not. And really, the main point of step 4 is to just ensure that for each step, there's at least one opening. That is, a cell that does not have a bottom wall. For step 5, we have 2 main choices: to continue or complete the maze. If we choose to continue and add another row, we will continue with the following steps. Output a copy of our row below the current row. Remove all right walls. Remove cells with a bottom wall from their set. Remove all bottom walls. Continue from step 2. Now, remember that step 2 is join any cells not members of a set to their own unique set. Essentially, we're just going to assign each empty cell with its own new unique set. And now we basically just continue in the same order we did previously. We move on to step 3, step 4, and step 5. And if we want to keep making more rows of the maze, then we will repeat back to step 2. Now I'm going to complete the rest of the rows just before the last row. Now, if we decide to end the maze, instead of adding a new row, we will continue with the following steps. Output the current row. Add a bottom wall to every cell. Moving from left to right. If the current cell and the cell to the right are members of a different set, remove the right wall. Union the sets to which the current cell and the cell to the right are members. Output the final row. So I'm actually going to use the visuals from the website because my own visuals failed to show some of the steps. But what you're seeing right now is an example of a bottom row. And we're looping over each cell, going from left to right. And the most important step is this one, where you see the middle wall is actually saved after joining the 2 cells. And if we look back, this is because it was actually 3 and 3. So they had the same cell value, but they had a wall in the middle. So this is the only instance where you don't tear down the middle wall. And that's about it. 5 fairly simple steps, which will always produce a perfect procedural non-finite maze. If any steps did not make any sense or cause you confusion, I would suggest looking over the explanation from the link in the description. Or please let me know in the comments and I'll try my best to help you out. Also, from here on out, the videos in this series are going to be a lot less scripted, edited, and more freeform. I feel that style fits the actual programming a lot better and it's a lot less work, so hopefully I can get these videos out faster for you guys. Again, this was just the intro and explanation of the algorithm, so stick around. The next video should be out in a couple of days where we'll actually begin programming. Until then, thanks for watching and I'll see you guys soon.